The Great Pyramid stones fit together with machine-like precision, yet no blueprint has ever been found. How did ancient builders achieve this without a single written plan? This is the central mystery we will solve. By the end, you will understand the 10 ingenious principles that formed a complete, unwritten engineering system, turning impossible monuments into reality. We will uncover how master artisans used their hands as measuring tools and why entire societies could coordinate like a single mind. What does this lost art of building reveal about the true nature of human ingenuity? That master mason's hands tell a story no blueprint ever could. His fingers, calloused and precise, move across the surface of a granite block not to measure inches, but to feel its soul. They trace the grain, sense a hidden weakness, identify the perfect line for a strike. This is not guesswork. It is a deep, wordless conversation with the stone itself, a form of intelligence so fundamental it often escapes our notice. This is what scholars call tacit knowledge. It is the immense reservoir of understanding that lives in our muscles, our senses, and our intuition, far beyond what can be written down in a manual. Think of riding a bicycle. You can read 100 books on balance and physics, but that knowledge alone will not keep you upright. You learn by doing, by feeling the subtle shifts in your weight, by experiencing the moment the machine becomes an extension of yourself. The ancient builder's relationship with stone was precisely this intimate. Philosopher Michael Polanyi captured this perfectly when he stated, "We can know more than we can tell." The master craftsman knew exactly how a limestone block would fracture under a specific angled blow. He could hear the difference in the ring of a hammer strike that meant the stone was ready to split cleanly. He could judge the perfect consistency of mortar by its feel, not by a written recipe. This knowledge was his true blueprint, etched not on papyrus, but into the very pathways of his nervous system. So how was this profound, silent expertise passed from one generation to the next? It required a living curriculum, one taught in dust and sweat. A young apprentice did not start with theory. He began by watching. For years, he would stand beside the master, observing the set of his shoulders, the rhythm of his hammer, the way he squinted at a shadow along the stone's edge. Then came the mimicry. He would be given simple tasks shaping softer stone, mixing plaster, receiving immediate, often wordless correction. A grunt of approval, a guiding hand repositioning his grip, a demonstration of the correct motion. This was a total education of the body and mind in unison. Through countless repetitions, the apprentice's hands began to learn what his conscious mind could not yet articulate. The correct force, the ideal angle, the intuitive read of the material, all of this seeped into him through experience. This system created something far more resilient than a library of scrolls. It created a living library of human skill. Each master builder was a walking repository of techniques, and each successful apprentice added his own refinements. This chain of tacit knowledge, passed from hand to skilled hand, ensured that the most complex construction methods could survive for centuries. The designs lived not on a shelf, but in the collective muscle memory of the community. Yet the human body, for all its genius, has limits. To translate this deep, felt understanding into the monumental scale of a pyramid or a temple, these builders needed to extend their senses. They needed to create physical tools that could act as bridges, turning intimate tactile knowledge into shared, colossal reality. The master's hands could feel perfection, but how could that feeling be shared with 100 other masons across a vast worksite? The answer begins with a single, silent teacher, a physical object of profound simplicity, the master template. Imagine a wooden board or a carefully shaped stone block, its edges and angles carved to absolute perfection. This one object held the entire design for 1,000 others. Instead of instructing each worker to measure and calculate independently, the master builder would present this template. Every subsequent stone would be dressed or shaped until it matched this ideal model exactly. This is the first principle modular design through master templates, and it is the cornerstone of turning intimate skill into colossal, repeatable precision. Look at the breathtaking walls of an Inca fortress. The stones, though irregular in shape, fit together with such tight, interlocking seams that not even a blade of grass can slip between them. This was not achieved by magically shaping each unique stone to its unique neighbor. Archaeologists believe the builders used a system of master templates. They would have carefully shaped one perfect stone for a key corner or a specific wall section. That stone became the standard. Other masons, perhaps working at different quarries or on different parts of the site, would use simple copies or guides based on that original to produce components that were functionally identical. The genius is in the replication. Once that perfect form was established, the challenge was no longer one of endless design, but of faithful copying. This modular thinking revolutionized the building process. It allowed for a powerful division of labor. One team could be dedicated solely to quarrying rough blocks. Another, using the master templates, could focus exclusively on the precise dressing and shaping. A third group could be responsible for the final assembly, trusting that every piece they received would fit its predetermined place. This is how you coordinate the work of thousands without a single written schedule. It turns a chaotic project into a predictable, almost mechanical production line. The Roman arch provides another perfect example. The voussoirs, the wedge-shaped stones that form the arch, all look unique to the untrained eye, but in reality, they follow a strict modular pattern based on the arch's radius. A set of templates would define the tapering shape, and each stone would be cut to match its specific position's template. The result, when the final keystone is dropped into place at the apex, the entire structure locks together under its own weight, a testament to systematic replication. This principle reveals a profound insight. Precision in the ancient world was often less about measuring each piece from scratch and more about perfecting a system of copying. The master template was a bridge. It translated the abstract geometry in the master builder's mind, refined through his tacit knowledge, into a physical, tangible standard that anyone could use. It democratized precision. A young apprentice, still years away from understanding the underlying mathematics, could still produce a perfectly shaped block simply by following the guide. This approach transformed an intellectual puzzle into a tactile, repeatable task. It shows us that the builder's true innovation was not in making one perfect thing, but in creating a method to make 10,000 perfect things, all from one perfect idea. And to create and use these templates, they relied on a universal language far older than any written word, the silent, undeniable logic of geometry. Geometry is the silent language spoken by every stone in these ancient sites. It was not a theoretical science confined to scrolls, but a living, breathing toolkit used on the worksite every single day. This is the second principle, the sophisticated use of geometry and proportional systems. Forget complex equations on a chalkboard. For these builders, geometry was a physical act. Picture a worker hammering a stake into the ground, tying a length of knotted cord to it and pulling it taut. With a simple sweep, he could inscribe a perfect circle on the earth, laying out the foundation for a temple or a ceremonial plaza. Or envision a team using 3 rods of specific lengths, arranged to form a triangle. If the sides are in the sacred ratio of 3, 4, 5, they have just created a perfect right angle, large enough to square the corner of a massive pyramid. These were not mere tricks, they were the applied mathematics of monument building, turning abstract relationships into tangible, scalable forms. These proportional systems were often considered sacred, woven into the cultural and spiritual fabric of a society. The Egyptians had the royal cubit, a standard unit of length embodied in a physical rod of wood or stone. This cubit was subdivided into palms and digits, creating a consistent measuring system that could be replicated anywhere. But the system went deeper. They used fixed ratios like the sect, which defined the slope of a pyramid's face. A builder did not need to calculate the angle for each block. He simply needed to know the sect ratio, perhaps remembered as a chant or a ritual phrase, and apply it using his measuring cords and sighting tools. The result was a perfect, uniform incline rising toward the heavens. Similarly, the Maya designed their soaring temples using precise astronomical alignments and complex geometric patterns that were encoded into their worldview. The proportions of a doorway, the height of a platform, the layout of a city, all could be derived from a set of memorized rules and cyclical calendars. This use of sacred geometry served a dual purpose. First, it provided an unwavering mental and physical framework. Every builder, from the master architect to the apprentice stone dresser, was working from the same invisible blueprint of proportions. This ensured that a component shaped at a distant quarry would still fit perfectly into the grand design upon arrival. Second, it infused the structure with meaning. The building itself became a manifestation of cosmic order, a bridge between the earthly and the divine. The harmony perceived by the eye, the feeling of balance when standing before these structures, stems directly from this rigorous application of proportional systems. The builders were not just stacking stones, they were composing a symphony in stone, where every element related to every other through a consistent, beautiful logic. This approach eliminated the need for endless custom fitting. Once the overall proportional scheme was established, the work became modular and predictable. The focus shifted from solving a unique problem with each stone to executing a predefined pattern with flawless repetition. Geometry, therefore, was the great translator. It converted the master builder's visionary design and deep tacit knowledge into a set of simple, repeatable rules that hundreds of hands could follow. It transformed intuition into institution and wonder into a workable plan. Yet, even with perfect templates and sacred geometry, a monumental project faces its most chaotic challenge, the moment of assembly. How do you coordinate the movement of thousands of multi-ton blocks and the labor of countless individuals across a sprawling landscape without a single foreman's clipboard? A taut cord and a hanging weight may seem insignificant against a mountain of stone. Yet these two simple tools, the cord and the plumb bob, were the relentless guardians of ancient accuracy, the portable truth against which every wall and corner was measured. They translated the grand vision of geometry into a language of immediate physical feedback. Picture a team of builders preparing a massive limestone block. They would stretch a cord soaked in red ochre or another pigment tightly across its surface. With a quick snap, the cord would strike the stone, leaving a perfectly straight, vivid line as a guide for the mason's chisels. This was the snap line, a tool of breathtaking simplicity that could mark a straight edge 20 feet long as easily as 2. It meant that precision was not a rare, hard-won achievement, but a repeatable, everyday act. The plumb bob worked in silent partnership with the cord. This was nothing more than a pointed weight, often of stone or metal, suspended from a string. But when held against the rising face of a wall, it became an oracle of the vertical. Gravity itself, that universal and unforgiving force, would pull the string into a perfectly straight line. Any deviation in the wall's construction would be instantly revealed by the gap between the string and the stone. This constant, real-time checking created a physical dialogue between the builder and his creation. He was not working from a distant memory or a fragile diagram. He was in continuous conversation with the structure itself, receiving an immediate answer to a single, vital question: is it true? This reliance on direct physical verification embedded quality control into the very rhythm of the work. A mason did not shape a block in isolation, hoping it would fit later. He checked his progress constantly against the chord for straightness and the bob for square. A team assembling a wall would use these tools at every course or layer of stone. This process meant that errors could not accumulate. A tiny mistake in one layer would be caught and corrected before the next stone was laid, preventing a small flaw from becoming a catastrophic failure 50 feet higher. It was a system of built-in resilience where the tools themselves enforced the standard. This constant physical dialogue naturally evolved into more sophisticated setting-out techniques. Builders began using grids of chords or multiple plumb lines to transfer complex alignments from a master plan on the ground to the growing structure above. The humble chord and bob became the physical threads connecting the sacred geometry in the architect's mind to the emerging, colossal reality of stone. But even with perfect lines and true walls, another profound challenge remained. How do you manage the movement of thousands of multi-ton blocks and the efforts of an entire society without a single written instruction or foreman's schedule? The final, breathtaking precision of these walls was not born from a single, perfect cut. It emerged from a patient, physical conversation between mason and stone, a dialogue of trial and error conducted at a monumental scale. This is the third principle, dry fitting and iterative adjustment. Envision the scene on the rising platform of a pyramid. A team of workers using ramps and ropes maneuvers a multi-ton granite block toward its designated spot. They do not simply lower it and hope for the best. Instead, they perform a dry fit, setting the stone carefully into place without any permanent mortar. Then they listen, they look, they search for the faintest sliver of light between the new block and its neighbors. They might even use a soft, colored clay smeared on the contact surfaces. When the block is lifted away, the clay remains only on the high spots, the areas that made contact. These telltale marks become a precise map for the next step. With stone hammers and abrasive sand, the masons would then dress down those highlighted areas, removing just a few grains of stone at a time. Then the cycle repeats. Lift, test, mark, adjust. This was not a sign of imprecision, but the very heart of achieving it. The building site transformed into a vast, open-air workshop where the final, perfect fit was not preordained by a blueprint, but discovered through relentless physical interaction. This iterative process reveals a philosophy of craftsmanship fundamentally different from our modern world of prefabrication. Today, we expect components to arrive on site perfectly formed, ready to slot into a digital model. The ancient builders' approach was more responsive, more humble before the material. They acknowledged that stone, even from the same quarry, could have hidden variations. They understood that the true plane of perfection existed in the relationship between the stones themselves, not just on a theoretical drawing. By dry fitting, they allowed the materials to guide them to the final solution. This method required immense patience and a deep trust in the process. It meant that progress could seem painstakingly slow, as each block underwent multiple cycles of adjustment. Yet, this very slowness guaranteed the legendary accuracy we marvel at today. The sound of stone grating against stone was not a noise of failure, but the sound of the structure teaching the builders how it wanted to be assembled. This hands-on, responsive intelligence ensured that errors were not just corrected, but absorbed and refined into the whole, creating a seamless unity that feels almost organic. It was a form of three-dimensional puzzle solving, where the puzzle pieces themselves were gently shaped until they whispered into place. The calm surface of a pond holds a secret truth, a perfectly level line drawn by nature itself. Ancient builders learned to listen to this silent teacher, mastering the fourth principle, harnessing natural forces for precision. While the Plumb bob conversed with gravity to find the vertical, they needed an equally reliable partner to define the horizontal across acres of uneven ground. Their solution was as elegant as it was effective: the water level. Imagine a long, shallow trench dug along the intended foundation line of a great wall. Workers would fill this trench with water, then wait for the ripples to settle. No matter how the land rose or fell beneath it, that water surface would always find a perfect, unwavering level. By measuring down from this liquid plane at multiple points, teams could mark identical height benchmarks on stone pillars or stakes driven into the earth. These marks became the shared reference, the common datum, for every builder on the site. The principle scaled beautifully. For longer distances or more complex layouts, they used interconnected vessels. A series of pots or troughs, linked by channels or siphons, would be placed across the terrain. Once filled, the water in each container would settle to exactly the same height, creating a network of level points that could span an entire city plan. This is how the colossal platforms for Mesoamerican temples were made perfectly flat, and how the long, gentle gradient of a Roman aqueduct was maintained with such exactitude over miles. The water level did more than just guide construction. It embedded a profound philosophical insight into the work. The builders were not imposing an abstract grid upon a reluctant landscape. They were using a fundamental law of the physical world, the behavior of fluids seeking equilibrium, to find harmony with the site. They were working with their environment, not against it. This tool democratized a complex engineering task. Establishing a true level over long distances is a formidable challenge, even with modern lasers. Yet with water, sand, and simple observation, a crew of laborers could achieve it. It turned a geometric abstraction into a tangible, visible guide. A foreman could point to the water line in a trench and say, "Build to here," and every team working on separate sections would be unified by that single, liquid command. This shared reference was the glue that held a decentralized project together. It ensured that when separate teams finished their segments of a massive foundation, those segments would meet seamlessly because they all originated from the same calm, unwavering plane of water. It was a system of silent, natural coordination, but establishing a level plane was only half the battle. The true test of a builder's wisdom came from understanding the very soul of his materials, knowing not just how to shape stone, but how different stones would behave for centuries under the immense weight of a monument. The stone itself was the first and most important teacher. Before a single chisel struck, an experienced quarry master would walk the scarred landscape of the excavation site, his eyes reading the bedrock like a map. He was not just looking for rock, he was searching for the right rock. This deep, intuitive understanding of materials, the fourth principle of material intelligence and selective quarrying, meant that precision was not created at the building site, but chosen from the earth itself. Quarry was a library, and each layer of stone told a different story. A master builder knew that limestone from a lower, denser stratum was perfect for foundational blocks, bearing immense weight without crushing. A higher layer, perhaps finer grained and more consistent, was ideal for the intricate carving of a temple facade. He could identify granite with a uniform crystalline structure, less likely to develop hidden fractures that could shatter under stress years later. This knowledge was accumulated over generations, a catalogue of strengths and weaknesses passed down through stories of success and, crucially, of failure. It was a science of observation written in the very geology of the land. This material intelligence dictated everything about how a stone was handled. The most critical decision was the direction of the cut relative to the stone's natural bedding plane. Think of sedimentary stone like a stack of paper. If you try to split it parallel to the sheets, it separates cleanly along its natural weakness. But if you need a strong, load-bearing block, you cut perpendicular to that grain across the sheets, harnessing the stone's inherent compressive strength. Quarry workers used this knowledge strategically. They would locate natural fissures, then drive wooden wedges into them. By soaking the wedges with water, the wood would expand with tremendous, gradual force, persuading the stone to split exactly along the line nature had already suggested. This was not a violent act but a cooperative one, working with the material's own logic to release a perfectly shaped block with minimal effort and waste. This symbiotic relationship with the earth solved problems before they ever reached the construction platform. By selecting the ideal stone for its specific task, a dense basalt for door lintels, a softer sandstone for detailed reliefs, builders dramatically reduced the risk of later failure. A block cut with a grain for stability would not suddenly crack under the weight of the course above. A carefully chosen facing stone would weather centuries of wind and rain without eroding. This forethought was a form of embedded efficiency. It meant less time spent later on correcting flaws, less material wasted on doomed attempts to fit an unsuitable stone, and a final structure whose longevity was designed into its very bones. The quarry master's choice was the first and most vital cut, setting in motion a chain of precision that would culminate in those breathtaking, seamless walls. It reminds us that for these builders, the monument was not an imposition upon the landscape, but a collaboration with it, a dialogue that began deep within the earth and rose, block by intelligent block, toward the sky. The rhythm of creation on these ancient sites was not a roar but a persistent, patient percussion. It was the tap, tap, tap of a stone hammer, a sound that echoed for generations. This is the art of pecking and abrasion, the fundamental dialogue between human intention and unyielding material. Before a block could find its place in a perfect wall, it had to be spoken to in this language of gradual persuasion. The process began with a technique as simple as it was effective: pecking. A worker would take a hammerstone, often a piece of harder rock like dolerite, and use it to strike the surface of a granite or limestone block. With countless controlled blows, he would fracture away tiny fragments, slowly roughing out the desired shape. This was not hacking or smashing. It was a careful, incremental reduction, like a sculptor finding the form within the marble. The sound of this work was a constant, rhythmic heartbeat across the quarry and worksite, a testament to the sheer will required to shape the earth. But a pecked surface was still rough, unsuitable for the hairline joints we marvel at today. To achieve that seamless fit, the builders moved to the next phase: grinding. They would use a simple yet brilliant combination: sand, water, and a flat abrasive stone. By sprinkling quartz sand, a material harder than most building stones, onto the surface and then rubbing with another stone or a wooden plank, they created a natural sandpaper. The addition of water turned the mixture into a slurry, which both lubricated the process and carried away the ground stone particles, revealing a fresh surface beneath. This method granted them astonishing control. By using finer and finer grits of sand, they could progress from a rough grind to a perfectly smooth, almost polished face. The final surface was so true that when two blocks were placed together, their contact was nearly total, distributing weight evenly and creating those legendary joints. The genius of this two-stage process lay in its incremental nature. Because material was removed so slowly, a mason could make minute, continuous adjustments. He could feel the stone's resistance change, see a high spot gradually disappear, and correct any deviation long before it became a major flaw. This hands-on, tactile feedback loop was essential. It meant that precision was not a final destination checked at the end, but a quality maintained throughout the entire journey of shaping. The artisan developed an intimate connection with his material, learning its hidden grain and subtle hardness through the vibrations in his hands and the changing sound of the grind. This was where patience became a measurable engineering virtue. A single block could take weeks or even months to dress to perfection. Yet this very slowness was the source of its strength and accuracy. It was a meditation in stone, where the gradual removal of material was not wasted time, but the essential process of bringing a chaotic natural form into geometric harmony. Each finely worked piece, born from this rhythm of tap and grind, was now ready. But a collection of perfect stones is not yet a monument. The next great puzzle awaited, one of logistics and coordination on a scale that defies belief. That final, perfect stone is not the end of the story. It is the beginning of a silent conversation with gravity itself. The true genius of these builders is revealed not when a block sits alone, but when it becomes part of a whole that defies collapse. This is the fifth principle: keystone logic and structural self-locking. Think of a simple arch. Each wedge-shaped stone, called a voussoir, is shaped with meticulous care. But on its own, it is unstable, prone to slipping and falling. The magic happens only at the moment of final assembly. When the last piece, the keystone, is lowered into the very top, something extraordinary occurs. The weight of the entire structure above is transformed. It is no longer a burden pushing down, but a force pushing outward and downward, channeled through the precise geometry of each stone. The stones press against their neighbors, transferring load along the curve of the arch and down into the solid supports on either side. The arch locks itself together under its own weight. The precision of the fit is not just for beauty, it is the very source of its strength. A tiny gap would allow movement, a shift in the force, and the entire elegant system would fail. This understanding of compression, of designing components that only become stable when united, represents a pinnacle of engineering intuition. Builders grasped this not from complex equations, but from physical experimentation. They likely built small-scale models out of wood or stone, testing shapes and angles. They learned through trial and error how to direct lines of force along desired paths. This knowledge was then scaled up into breathtaking reality. The corbelled arches of Mycenaean tombs or Maya temples work on a similar principle of self-locking geometry. Each stone is laid so that it projects slightly inward over the one below. Gravity pulls it downward, but the overlapping design prevents it from falling inward, creating a stable, stepped vault. The entire structure is a balanced equation of mass and counter-thrust. This principle meant that the builder's goal was not merely to place stones, but to choreograph forces. The precise angle of each voussoir's face, the exact taper of a corbel, these were calculated through experience to ensure that when the final piece was set, the entire assembly would sigh into a state of perfect, permanent tension. It was a marriage of form and function so complete that the aesthetics we admire, the graceful curve, the imposing span, are simply the visible expression of invisible physical laws at work. The structure itself became its own blueprint, a physical demonstration of stability that could be observed, understood, and replicated. This self-locking logic provided a powerful kind of built-in safety. Once complete, such a structure actively resisted disintegration. It wanted to stand. This inherent stability is why so many arches and vaults have survived earthquakes, wars, and centuries of neglect. The builders did not just create monuments, they created stone puzzles that, when solved, became eternal. These self-locking structures stand as a testament to a universal engineering truth. Yet one culture perfected a method that seems to turn logic inside out. The walls of Sacsayhuaman are a silent symphony in stone, a puzzle of colossal, irregular blocks fitted together with a precision that feels almost supernatural. Here, there are no repeating modules, no uniform arches, just a breathtaking mosaic of giant granite pieces, each uniquely shaped, each locking perfectly with its neighbors without a trace of mortar. This Inca enigma presents a fascinating contradiction to the modular systems we have explored, showcasing a problem-solving philosophy rooted in supreme adaptation. The prevailing theory to explain this marvel is known as bedding or soft-fit construction. It is a process of profound patience and physical dialogue. Imagine a team preparing to set a massive, multi-ton stone. Instead of meticulously shaping it to a predetermined template on the ground, they would roughly dress it to an approximate size and shape. Then, using earth ramps and levers, they would carefully lower this upper stone onto the one already in place below. Between them, they would have placed a layer of abrasive sand. The immense weight of the stone itself became the tool. By rocking the block or perhaps lifting and dropping it incrementally, the two surfaces would grind against each other, the sand acting as a natural milling agent. Over countless repetitions, the lower stone would gradually wear away to receive the exact, unique contours of the upper one, and vice versa. They were not cutting to a line, they were allowing the stones to find their own perfect fit through a slow dance of friction and pressure. This method likely involved a complementary process of selective carving. After several grinding cycles, workers might lift the upper stone to examine the contact surfaces. Areas showing the most wear, indicated by the smoothed sand, revealed the high spots preventing full contact. Using simple stone tools, they would then peck away at these specific points on the lower stone, creating a more precise socket. Then the grinding would resume. This cycle of lower, grind, lift, and selectively carve, repeated over and over, resulted in that legendary interface where the two stones conform to each other so completely that they essentially become one. The seam between them is not a gap but a complex three-dimensional fingerprint of their union. The genius of this approach is its brilliant response to the environment. The Andes are a land of immense seismic activity. A rigid, modular wall with straight, continuous joints would be vulnerable to cracking and collapse during an earthquake. But this polygonal puzzle is inherently flexible. When the ground shakes, the irregular, interlocking stones can shift and rock slightly within their custom-fit sockets, absorbing and dissipating the energy without fracturing. The wall moves as a dynamic, unified mass, then settles back into place. The structure is not fighting the forces of nature, it is designed to move with them. This represents the pinnacle of material intelligence, a building philosophy that listened to the land itself. It was not about imposing an abstract geometric ideal, but about discovering the perfect fit through direct, relentless physical conversation, creating walls that were not just built, but grown from the very bedrock of necessity. The final, perfect fit between two stones was a triumph of local knowledge, but a monument is a world in itself, demanding a vision that encompasses the whole. Before the first foundation was ever dug, that vision had to be translated from mind to earth. This brings us to the sixth principle, the use of full-scale layouts and ground plans. Picture the cleared, leveled ground of a sacred site. Instead of parchment or clay tablets, the master builders used the earth as their drawing board. With a network of ropes stretched taut between wooden stakes, and perhaps lines drawn with colored powders or ochre, they would physically articulate the entire footprint of the coming structure at a 1-to-1 scale. Every wall, every column, every doorway was outlined in real dimensions upon the soil. This was not a sketch, it was a life-sized prototype, a communal map written in rope and earth. This full-scale layout served as the ultimate shared reference. For the master architect, it was a chance to walk the plan, to feel the proportions with his own steps, and to make crucial adjustments before any irreversible work began. He could sight along the rope lines to check alignments with celestial markers or other buildings, ensuring the temple would hold its proper place in the cosmos. For the hundreds of workers, this physical diagram was their constant guide. A stone dresser at a quarry miles away could be told his block was destined for the north wall, between the third and fourth stake markers, and he could understand its place in the grand scheme. Teams laying foundations had an unambiguous target, their trenches following the precise lines laid out on the ground. We see evidence of this practice across cultures. In the sprawling temple complexes of ancient Egypt, archaeologists have found remnants of such ceremonial layouts, where the sacred axes and dimensions were first established with ritual precision. The master builders of Gothic cathedrals in medieval Europe employed the same method. On the flattened floor of a stone tracer's lodge, or directly on a leveled foundation platform, they would incise the full-scale geometric patterns for a rose window or a complex vault directly onto the surface. These lines, known as tracing floors, allowed artisans to fabricate each uniquely shaped stone to fit its exact position in the three-dimensional puzzle, all guided by the two-dimensional master plan beneath their feet. This practice transformed abstract design into tangible, collective action. The ropes and stakes were a language everyone could understand, transcending literacy or specialized training. They created a shared physical reality that aligned every team, from the quarrymen to the masons to the laborers moving materials. Coordination was achieved not through a stack of documents held by a single foreman, but through these persistent public markers that kept the ultimate goal literally underfoot. It democratized the blueprint, making the grand vision a daily, visible presence for all. The building did not emerge from a secret set of instructions, but from a common map drawn upon the very ground it would occupy, a profound act of turning earth into intention. Yet, even with a perfect plan laid upon the ground, a new challenge arose with every course of stone added upward: how to ensure the vision remained true as it ascended into the sky, far from the guiding lines below. Hidden from the final glory of the finished wall, on the underside of a massive block or along its rough-hewn side, lies a quiet signature of the building process. A single chiseled line, a sequence of dots, a painted arrow in faded red ochre. To the untrained eye, these are mere blemishes, the incidental scars of construction. But to the mason who placed them there, they were a vital message, a necessary word in a silent language that organized chaos. This is the world of mason's marks, the seventh principle, a non-verbal communication system that turned thousands of unique stones into a coherent, rising whole. These marks were the personal notes of the builders, etched directly into the material of their work. They served a multitude of practical purposes, each one a crucial piece of logistical data. Some were simple quarry identifiers, a symbol denoting which specific rock face or team the block originated from, allowing for accountability and perhaps even a form of ancient quality tracking. Others were directional arrows or alignment marks, indicating which edge of the stone should face north or which surface was meant to be the finished exterior. This prevented a beautifully carved block from being installed upside down or facing inward, a catastrophic error when dealing with multi-ton granite. Perhaps the most ingenious marks were assembly codes, in structures composed of complex, interlocking pieces, like the vaults of a Gothic cathedral or the precisely tapered stones of an arch. Each block was essentially unique. A simple numbering system, often using tally marks or repeated symbols, told the builders the exact sequence for installation. Stone number 7 belonged directly between stones 6 and 8. This transformed the terrifying puzzle of a massive construction site into a manageable, step-by-step process. A team high on the rising wall could call for the next piece by its mark, and the crew below could locate it among the seeming chaos of the stockyard, knowing it would fit perfectly. This system created a bridge between the individual craftsman and the collective endeavor. The stone dresser, working alone or in a small team, would carve his mark into a block once his part was complete. It was a signature of responsibility, but also a handing-off point. That mark released the stone into the larger system, carrying with it all the necessary information for the next phase of its journey. The assembly crews did not need to be master sculptors themselves. They simply needed to understand this basic symbolic language. They became readers of stone, following the instructions left for them by their predecessors. The efficiency of this is profound. It eliminated the need for constant verbal instruction or supervision for every single action. The marks themselves did the directing. They were a persistent, error-proof form of memory that survived dust, noise, and the passage of time on a busy site. A foreman could walk the lines of prepared blocks and, by reading their symbols, understand the entire state of readiness for a section of wall. This hints at a level of project management and logistical foresight that we often don't attribute to ancient cultures. They were not just moving rock, they were managing information flow in a physical, durable format. We see echoes of this system across millennia and continents. In the pyramids of Giza, stones bear marks thought to indicate work gangs like the famous Friends of Khufu crew. In medieval European cathedrals, intricate personal symbols identified the mason who carved a specific gargoyle or capital, ensuring he was paid for his work. In the great Inca structures, while less studied, subtle notches and protrusions may have served similar guiding purposes during the mind-bending dry fitting process. The specific symbols changed, but the need for this silent dialogue between maker and installer was universal. This language of stone reveals the builders as pragmatic problem solvers of the highest order. They faced an immense coordination challenge and invented a simple, elegant solution, writing their instructions not on perishable parchment, but on the very bones of their creation. It was a way of embedding intelligence into the project itself, making the building site not just a place of labor, but a place where stone could speak, telling each worker exactly where it belonged in the grand design. And to ensure that every speaking stone arrived at the right place at the right time, an even broader system of coordination was required, one that orchestrated the rhythm of an entire society. The silent language of masons' marks organized the chaos of the workyard, but the stones themselves held another, more subtle voice. A master builder would sometimes lean close to a newly shaped block and give it a sharp, precise tap with his hammer. He was not just looking, he was listening. The sound that echoed back was a secret report on the stone's very soul. A clear, bright ring signaled a block of solid, flawless integrity, its internal structure uniform and strong. A dull, flat thud, however, could betray a hidden crack, an internal flaw that might cause the stone to fail under the immense weight of the courses above. This practice, acoustic testing, represents the seventh principle, where the ear became as vital a tool as the eye or the hand in the quest for perfection. It was a form of non-destructive evaluation, a way to peer inside the stone without breaking it apart, using vibration and resonance as a diagnostic tool. This sensory skill was a profound extension of tacit knowledge, an intuitive understanding of how sound travels through material, learned through a lifetime of listening. The concept goes beyond simple quality control for individual blocks. Some researchers have proposed a fascinating possibility regarding the most exquisitely constructed chambers, like the King's Chamber in the Great Pyramid of Giza. The granite slabs that form its walls and soaring ceiling are fitted with such incredible precision that the joints are nearly invisible. It has been suggested that these massive stones might have been carefully selected and adjusted not just for a visual fit, but for an acoustic one. The idea is that the entire chamber could have been tuned, like a colossal musical instrument, to resonate at a specific frequency. When certain tones were chanted or instruments were played within the space, the room itself might have amplified and sustained those sounds, creating an overwhelming sensory experience. This blends the practical with the profound. From a purely engineering standpoint, a block that rings true is a block that will bear load predictably. Ensuring that all stones in a critical arch or vault shared similar acoustic properties would guarantee a uniformity of strength. But in a sacred context, this sonic harmony could have held deep ritual significance. The perfect ring of a stone might have been heard as a symbol of purity, its resonant frequency a way to connect the physical structure to celestial harmonies or the fundamental vibrations of the universe, as some ancient philosophies understood it. This auditory dimension reveals a holistic approach to craftsmanship where beauty, strength, and meaning were inseparable. The builder was not just an engineer, but something akin to a composer, listening for dissonance in his materials and seeking a final, silent chord in the assembled monument. It reminds us that for these cultures, a temple or tomb was not a silent shell, but a living space designed to shape experience, where light, space, and sound worked in concert to create awe. This pursuit of harmony in every sense required a final, overarching intelligence, one that could not be held in a single pair of hands, but had to live within the very rhythm of the society that raised these stones. But what of the forms that geometry cannot contain, the swirling vines of a Baroque capital or the delicate stone lace of a Gothic window? These are not built from straight lines and perfect circles, but from the flowing, organic logic of art. To create such complexity in unforgiving stone, some builders may have turned to a method of profound ingenuity, one that borrowed from the ancient art of the metalworker. This is the hypothesis of the soft prototype. Imagine a master sculptor faced with a rough block destined to become an intricate foliage carving. Instead of attacking the stone directly with only a mental image, he might first build up a layer of pliable clay or wax over the stone's core. In this soft medium, he is free to experiment. He can pinch, smooth, and sculpt the flowing curves and deep undercuts with his fingers, refining the form through pure tactile feedback until it feels exactly right. This malleable model becomes his true guide, a three-dimensional sketch made permanent not on paper but in space. Once satisfied, the artist then begins the meticulous work of subtraction. Using the clay or wax form as a direct reference, he carefully carves the stone away to match it, layer by layer. The soft prototype acts as a physical map, showing him exactly how deep to cut, where a curve should swell, and how a leaf should curl. This process is remarkably similar to the lost wax casting technique used for millennia to create bronze statues, where a wax model is encased in clay and then melted away to leave a perfect mold. Here, however, the wax or clay is not lost, but intentionally removed as the stone beneath is revealed in its final, perfected form. This approach elegantly solves a monumental problem: how to translate a fluid, artistic vision into rigid stone without complex mathematical plans. It bypasses the immense challenge of drafting such a three-dimensional shape in 2 dimensions. The sculptor does not need to calculate angles or project views. He simply needs to replicate what his hands have already created in a forgiving medium. It is a method of translation, turning the language of soft sculpture into the enduring speech of stone. We can see the potential for this in the repetitive ornamental elements of great cathedrals. A master could create one perfect prototype in clay for a specific type of rosette or finial. Apprentices could then press molds into this original to create their own wax or clay copies. Each worker, armed with an identical soft model, could then execute the carving on their own block of stone, ensuring stylistic consistency across hundreds of individual pieces that would later assemble high on the facade. This system merges artistic intuition with systematic replication. It acknowledges that some forms are born from feeling, not just from calculation. The soft prototype method reveals the ancient builder as both engineer and artist, someone who understood that the path to precision could sometimes be a winding, creative one. It suggests a workspace where materials conversed, where wax whispered to stone, guiding the chisel to uncover the beauty waiting within. This adaptive, hands-on intelligence ensured that even the most fantastical stone dreams could be given solid, lasting form. Yet the creation of perfect individual pieces, whether by template, geometry, or soft prototype, leads to the final and most awe-inspiring phase, the moment of assembly, where the silent coordination of an entire society was put to the ultimate test. The true scale of these projects becomes clear only when you see them not as structures but as societies. A pyramid did not rise from the genius of a single mind, but from the synchronized rhythm of thousands, each person a vital component in a living machine. This is the eighth principle, where social organization itself becomes the ultimate precision tool. The chief architect held the celestial vision, the sacred geometry that connected earth to sky. Beneath him, master masons translated that vision into the language of stone, overseeing teams of specialists. Quarrymen, with their intimate knowledge of the bedrock, selected and released the perfect blocks. Transporters, masters of leverage and friction, choreographed the impossible journey from quarry to site. Laborers, working in coordinated crews, moved earth and stone with a rhythm born of shared purpose. This was not a hierarchy of command, but a hierarchy of knowledge, each layer entrusted with a specific domain of expertise. The master did not need to teach a quarryman how to dress a facade stone, and the quarryman did not need to understand the astronomical alignment of the inner chamber. Each trusted the other's mastery, creating a system where specialized intelligence flowed seamlessly into a unified whole. This integration was sustained by powerful social technologies, primarily oral tradition and ritual. The grand design, the seeked ratio of a pyramid or the proportional system of a temple, was not written in a manual but memorized through chants, stories, and ceremonial recitations. These rituals did more than preserve data. They embedded the project's purpose into the cultural identity of every participant. A worker lifting a stone was not performing a random task. He was fulfilling a role in a story greater than himself, contributing to a legacy that would honor his community and his gods. This shared belief system transformed labor into a collective ceremony, aligning individual effort with a monumental goal. The result was a cooperative intelligence far surpassing what any individual or small group could achieve. The precision of the final monument is a direct reflection of this human framework, a testament to what becomes possible when a society organizes itself around a shared vision. It reveals that the most sophisticated tool in the ancient builder's kit was not made of copper or stone, but of trust, role, and ritual. This intricate social machine, however, faced its greatest test not in the routine, but in the unpredictable, when the plan met the stubborn reality of the earth. A Roman legionary engineer did not see a brick as just a brick. He saw a unit of empire. Where earlier cultures perfected methods, the Romans perfected systems, and their greatest innovation was the principle of standardization. This was not merely a building technique, it was a philosophy of control, enabling them to imprint an unmistakable order, the Ordo, across landscapes from Britain to Syria with breathtaking speed and consistency. The secret lay in modular thinking elevated to an imperial mandate. They established official, state-sanctioned sizes for everything from the common brick to the massive stone blocks of a fortress wall. A standard brick, for instance, could be easily produced in bulk at distant kilns, shipped anywhere, and used by any construction crew with the absolute certainty that it would fit. This turned construction into a kind of giant, predictable assembly kit. A soldier stationed on a remote frontier did not need to be a master mason. He simply needed to follow the established rulebook. This system is brilliantly encapsulated in the surviving work of Vitruvius, his 10-volume Texta Architectura. While this represents a move toward written codification, it is crucial to understand its role. Vitruvius did not write for the common laborer. He wrote for the educated master, the architectus, who was expected to possess a vast body of practical, tacit knowledge in addition to understanding these principles. The text served as a repository of best practices, a guide to proportions, materials, and machinery, ensuring that the institutional knowledge of Rome would not be lost. Yet on the ground, this knowledge was implemented by the most disciplined workforce in history, the Roman military. Legionary engineers were trained in standardized procedures, from laying a road to erecting an aqueduct arch. They moved with the army, bringing Roman order to newly conquered territory with methodical efficiency. Look at the repetitive, rhythmic arches of a Roman aqueduct marching across a valley. Each span is a repetition of a mastered form, built by teams following the same drill. Observe the grid plan of a colonial city, laid out with the same cardo and decumanous streets, regardless of the local geography. This was precision through replication at a continental scale. The Roman Ordo in architecture represents a pivotal bridge in our story. It sits between the world of purely tacit, experience-based knowledge passed from master to apprentice, and the world of formalized, written technical manuals. It shows how institutionalizing knowledge within a disciplined structure could achieve something new, rapid, large-scale construction that maintained high quality not through the genius of individual artisans, but through the unwavering application of systematic rules. The empire itself became the blueprint, and every standard brick was a silent soldier in its service. This systematic approach solved the problem of scale, but it invites a deeper question about the nature of the knowledge itself. If the Romans could write down so much of their engineering wisdom, does that mean the true secrets of the ancient builders were finally captured on paper, moving us out of the realm of mystery? The winter solstice sunrise does not simply shine upon Newgrange. It travels down its long, dark passage to ignite the inner chamber in a blaze of golden light. This was not a fortunate accident of construction, but its very purpose, a breathtaking demonstration of the ninth principle, astronomical alignment as a built-in guide. For cultures across the ancient world, the heavens provided the only truly fixed reference frame, a cosmic clock and compass of absolute reliability. By anchoring their most sacred structures to the sun, moon, and stars, builders created a giant, immutable tool for precision that spanned the horizon itself. The central axis of a temple, the corner of a pyramid, the doorway of a tomb, these were not placed by whim, but were carefully set to frame a specific celestial event, be it the solstice sunrise, the equinox shadow, or the rising of a particular star. This practice transformed the architecture into a permanent observatory, a machine of stone designed to capture a moment of cosmic alignment. The practical benefit was profound. Once that primary sightline was established, perhaps using nothing more than a simple shadow-casting gnomon, or a pair of aligned stakes observed over many seasons, it became the master reference for the entire construction. Builders could check the alignment of walls, platforms, and corridors against this celestial benchmark, ensuring the growing structure remained true to its original, sacred orientation. It was a way of borrowing the infinite precision of the cosmos to govern the finite work of human hands. At Chichen Itza during the equinoxes, the setting sun casts a shadow along the stepped edge of El Castillo that resembles a serpent slithering down the pyramid to meet its stone head at the base. This effect required an exact knowledge of the sun's changing path, and a building engineered to interact with that light in a very specific way. The pyramid itself became a calibrated instrument, its precision serving a dual purpose. Practically, it marked the agricultural cycles vital for survival. Spiritually, it demonstrated a harmony between the earthly and celestial realms, a divine order made visible through flawless construction. This embedding of cosmic order meant that the monument's accuracy was not just for its own sake, but was the physical expression of a deeper truth about the universe. The builders were not just stacking stones, they were aligning their world with the greater whole, creating a fixed point of connection between the community and the cycles that governed life, death, and renewal. The legacy of this principle whispers to us still, in the silent alignment of stones that wait, year after year, for the sun to fulfill its ancient appointment. A single man, working alone under the cover of the Florida night, moved stones heavier than those in the Great Pyramid. In the early 20th century, an eccentric Latvian immigrant named Ed Līdzkalnis began constructing what he called his coral castle, single-handedly quarrying, carving, and positioning over 1,000 tons of oolitic limestone. He claimed to have rediscovered the building secrets of the ancients, and his enigmatic achievement stands as a haunting modern echo of the principles we have been exploring. Leedskalnin's tools were deceptively simple, a collection of chains, ropes, metal tripods, and homemade winches fashioned from old car parts. Witnesses saw no cranes, no diesel engines, only the solitary figure of Ed and his rusted contraptions. The true secret, he often said, was not in the strength of machines, but in understanding the secrets of leverage and balance. He spoke of knowing the correct pivot point for any object, the precise spot where minimal force could achieve maximum effect. This is a pure, applied form of the ancient understanding of physics, where the builder becomes a partner with natural forces rather than their adversary. He reportedly used a simple tripod and chain block system, carefully positioning it so that the weight of the stone itself aided in its own movement. By rocking a multi-ton block ever so slightly and inserting a small rock as a pivot, he could change its direction. He would lift one end incrementally, place a slab underneath, then lift the other, walking the colossal piece across the yard with agonizing patience. His most famous feat involved a 9-ton revolving gate, so perfectly balanced on a truck axle that a child could push it open, yet so precisely fitted that it sealed without a gap. This was not magic, but a masterclass in applied mechanics, in the relentless iteration of trial and error, and in a profound tactile feel for his material. Leedskalnin's castle is a monument to one man's stubborn, intuitive grasp of principles that master builders have always known, that gravity, leverage, and friction are tools to be understood, not obstacles to be overpowered. His secretive nature and cryptic claims have fueled endless speculation about lost levitation techniques or supernatural aid. Yet, the more plausible explanation is perhaps the most powerful. It demonstrates that the core tenets of ancient engineering mastery, leverage, balance, material feel, and above all, persistent, focused effort never became obsolete. They simply waited in the quiet Florida night for one determined individual to listen to the stone and remember. The immense stone now rests at the foot of the wall, but its journey is only half complete. The final, most delicate act remains, coaxing this sleeping giant vertically into its precise socket, an operation demanding not brute force, but a symphony of applied physics. This is the 10th principle, the mastery of leverage, counterweights, and incremental placement, where the builders transformed themselves into human cranes through sheer mechanical ingenuity. Envision a team gathered around a granite block taller than a person. Long, stout wooden levers are slipped beneath one edge, resting on smaller stones that act as fulcrums. On a command, the crew throws their collective weight onto the levers. For a moment, nothing happens, the stones mass defying them. Then, with a collective groan of wood and a shower of dust, the colossal edge rises just an inch. Immediately, others slide flat stones or wooden wedges into the gap, locking in that tiny gain. They then reposition the levers, lift again, and insert more packing. Through this rhythmic, patient repetition, lift, pack, reposition, the entire multi-ton block is walked upward, inch by laborious inch. This technique, known as cribbing, allowed for astonishing control. It was a dialogue with gravity itself, a negotiation where every minor victory was secured before attempting the next. For the final, hairline adjustments, they likely turned to an even simpler tool, the inclined plane. A temporary ramp of earth and timber would be built alongside the rising course of stones. Teams would drag the new block up this slope until it hovered slightly above its destined spot. Then, using levers and a system of ropes perhaps threaded through a sturdier frame, they could pivot the stone with minute precision, aligning it perfectly with its neighbors before gradually lowering it by removing the packing from beneath. The sound in this final phase would not be shouts, but the focused silence of coordinated effort, punctuated by the creak of ropes and the soft tap of a hammer adjusting a final wedge. This entire process required a deep, intuitive feel for concepts a modern engineer would call the center of mass and the coefficient of friction. The master mover knew exactly where to place his lever to maximize its effect. He understood how a log roller would behave under load on different types of soil, and how much slope an earth ramp could bear before collapsing. This knowledge was not from a textbook, but from a lifetime of hands-on experience, from watching how stones behaved when they were tired, and learning to listen to the warnings of a straining rope. They were not just laborers, they were practitioners of a physical art, manipulating the fundamental laws of the universe with wooden tools and impeccable timing. The true testament to their skill is not that they moved the stones, but that they placed them with such care. The final act of lowering a block onto a prepared sand bedding or a dry fit neighbor was an exercise in supreme patience. Using a system of levers as a collective, organic hydraulic press, they could lower a stone with such gentle control that it kissed its neighbor without a crack, settling into a union that would last millennia. This macro-scale principle brings our exploration full circle. It connects the intimate, tactile knowledge of the mason's hand with the colossal ambition of the architect's vision. It reminds us that these monuments are not just feats of spiritual will or geometric genius, but also triumphs of practical, gritty, brilliant mechanics. The pyramid's peak was reached not in a single leap, but through millions of calculated, physical conversations between human intelligence and the stubborn mass of the earth. The rhythmic chant of 100 workers pulling a rope is more than a song, it is a living machine. In cultures where the written word was reserved for the elite or did not exist at all, the most vital engineering knowledge could not be entrusted to fragile scrolls. It had to be woven into the very fabric of daily life, encoded in stories, ceremonies, and the songs sung at the worksite. This cultural dimension reveals that the most sophisticated database for these builders was not a library, but their own shared traditions, where the line between a sacred ritual and a technical manual simply did not exist. Take the act of moving a colossal stone. Coordinating the pull of dozens of men on heavy ropes is an immense logistical challenge. A simple, mistimed heave could snap the ropes or crush a worker. The solution was likely found in the work chant. A lead singer or chant master would set a precise, driving rhythm through his lyrics. Each line, each beat, signaled the exact moment for the team to pull together. The chant became a metronome of muscle, synchronizing individual effort into a single, powerful force. The words themselves might have contained coded instructions, metaphors for grip, posture, or pacing, transforming a complex coordination problem into a memorable, repeatable performance. This knowledge was preserved not in a handbook, but in the community's musical repertoire, passed from one generation of workers to the next around evening fires, long before the next monument was ever conceived. Myths and legends served a similar, vital purpose. A story about a god who taught humans how to cut stone or a cultural hero who first discovered the secret of the arch was not mere fantasy. It was a narrative vessel for preserving a foundational technological breakthrough. By embedding the memory of an innovation within a sacred tale, the community ensured it would be retold, revered, and remembered. The myth provided a why, a divine sanction for the technique, while the act of recounting the story kept the conceptual knowledge alive. When a master mason referenced the god of craftsmanship while demonstrating an angle, he was not just sharing a belief, he was connecting a practical skill to an unbreakable chain of cultural memory, making it far more resilient than any isolated instruction. We see this principle in action during cornerstone ceremonies, which were common across the ancient world. The ritual of laying the first stone was often a public spectacle involving the community's leaders and priests. But within the prayers, offerings, and symbolic gestures lay deeply practical steps. The ceremony might have physically demonstrated the correct method for using a plumb bob to ensure the stone was true, or for using sighting rods to align it with a celestial marker. By performing these actions within a sacred context, the correct procedure was impressed upon all witnesses as not just good practice, but as a divinely mandated order. To deviate from it would be unthinkable both technically and spiritually. This fusion of the practical and the spiritual created a powerful, self-reinforcing system for safeguarding knowledge. Technical procedures became sacred duties. The right way to mix mortar or shape a voussoir was the holy way taught by ancestors and watched over by gods. This made the knowledge incredibly stable and resistant to careless change. An apprentice learned that precision was a form of piety and that his craft was a link in an eternal chain. The community itself became the guardian of its own engineering genius, with every festival, every story, and every song acting as a backup to the tacit knowledge in the master's hands. This reveals a profound truth about these societies. They understood that for knowledge to survive centuries, it must become more than information, it must become meaning. The monument, therefore, was not just the outcome of this system, it was its ultimate expression, a prayer built in stone, where every perfectly fitted block was a syllable in a long, remembered chant to the gods of order and permanence. The cyclopean walls of Mycenae and the stepped pyramids of Mesoamerica never exchanged a single idea, yet they speak the same silent language. Separated by oceans and millennia, builders from Greece to Peru arrived at eerily similar solutions, a phenomenon known as convergent evolution. It is as if the stone itself and the challenges of the earth whispered the same set of instructions to every culture that listened. This was not a shared secret passed along trade routes, but a universal response to universal problems. When your homeland shakes with earthquakes, you learn to build flexibly. The result in Peru is the interlocking polygonal puzzle of Inca masonry, and in Turkey, the similarly jigsaw-like walls of Hittite fortresses. Both systems absorb seismic energy by allowing stones to shift and settle without collapsing. The material itself dictated form. Cultures working with massive, hard-to-shape granite, like the Inca or the builders of ancient Japan's megalithic sites, often chose polygonal fitting. It was more efficient to spend time finding a unique lock between two irregular giants than to painstakingly dress them into perfect rectangles with primitive tools. Conversely, cultures with softer limestone or sandstone, like the Maya or the Egyptians, could more readily create standardized blocks and smooth, planar walls. The environment was the other great teacher. In regions of torrential rain, like parts of Southeast Asia and Mesoamerica, builders developed steeply sloped roofs and complex drainage, often using corbelled vault stones layered in stepping inward to create stable, dry interior spaces. The same corbelling principle appears in the burial chambers of Mycenaean Greece and the early pyramids of Egypt, solving the problem of spanning a roof with stone long before the true arch was perfected. This global survey reveals a shared toolkit emerging from necessity. The principle of modularity appears in the identical mud bricks of Mesopotamian ziggurats and the standard-sized blocks of Roman forts. The practice of dry fitting and iterative adjustment is seen in the trial placements of Japanese castle stones and the abrasive bedding of Inca walls. The logic of self-locking geometry is the foundation of both the Roman arch and the Maya corbelled vault. What we are witnessing is the fundamental pattern of human ingenuity. Faced with gravity, weather, and limited technology, the human mind, when connected intimately to its materials, tends to discover the same elegant solutions. The quest to build precisely, durably, and meaningfully without written plans was not a fluke of one gifted culture, but a common thread in our shared heritage. It reveals a deep, instinctual engineering intelligence, a convergent evolution of thought where the best answers were often written not on papyrus, but in the very pressures of the land and the stubborn reality of rock. A perfect seam between two stones is a triumph, but a single misaligned block tells a deeper story. For all their genius, these ancient systems of tacit knowledge and oral tradition carried inherent vulnerabilities, a delicate balance between fluid mastery and fragile continuity. The passing of a master craftsman was not just a personal loss, it was a potential crisis for an entire project. His hands held a lifetime of refined techniques, intuitive corrections, and nuanced judgments that had never been fully articulated. When he was gone, that unique repository of skill vanished with him. An apprentice might have learned the broad strokes, but the subtle art of reading a particular quarry's stone, or the exact feel for a mortar mix in the rainy season, could be lost, setting construction back years as a new generation struggled to rebuild that depth of understanding through trial and error. This reliance on living chains of knowledge also allowed for a slow, almost imperceptible drift in techniques over generations. Without a fixed written standard to act as an anchor, methods could evolve or simplify through practical necessity. A complex decorative carving might gradually become more stylized, its finer details softened as each new carver interpreted the master's template through his own slightly different lens. The very adaptability that allowed these systems to flourish across diverse landscapes also meant that replicating an exceptionally intricate or unique design, exactly as the original architect envisioned, became increasingly difficult with time. The famous slight curvature of the Parthenon stylobate, or floor, a subtle optical refinement, is a feat of such delicate precision that scholars debate whether it could have been perfectly reproduced by later builders working from the same oral and practical traditions. The design might live on, but its most exquisite subtleties could fade. We see evidence of this in the settlements and cracks that occasionally mar even the greatest structures. A foundation that sinks slightly, a course of stones that drifts out of perfect alignment. These are not merely signs of age. They are the fingerprints of human judgment under immense pressure, moments where collective experience met an unforeseen challenge in the substrate, or perhaps a lapse in the rigorous checking rituals. The occasional block that sits a fraction out of plane reminds us that these were worksites filled with people, not machines operating under the sun and the weight of time. These imperfections are not failures but honest markers of the process. Understanding these limitations does not diminish the achievements, it grounds them in reality. It helps us see these monuments not as magical or alien, but as hard-won victories within a specific technological and social context. They represent the pinnacle of what a culture could achieve by coordinating human intelligence, sensory acuity, and communal memory on a colossal scale. Their occasional flaws highlight the resilience of the overall system, which was designed to absorb small errors without catastrophic failure, and also its poignant fragility. The knowledge that built them was as durable as the stone it shaped, yet as perishable as the human voice that carried it from one generation to the next. This delicate balance between enduring stone and ephemeral knowledge leads us to a final, powerful question. What does this ancient, hands-on intelligence have to say to our own world of digital blueprints and automated construction? The seamless joints and colossal stones whisper a tantalizing possibility to the modern mind, one that feels easier to accept than the truth. It is simpler to believe in a single, magical explanation, a vanished super science or visitors from the stars, than to comprehend the vast, patient, human effort these monuments truly represent. These popular myths, however captivating, collapse under the weight of the evidence we have just walked through. The real story is written in the mundane, tangible clues left behind. It is in the quarry where thousands of stone hammers were found, worn down from years of pecking. It is in the trial and error bedding marks visible on the underside of Inca blocks, the literal grind of stone on stone. It is in the remnants of earthen ramps, the post holes for wooden cranes, and the mason's marks that directed a human team. there is no evidence of a mysterious, lost technology, only overwhelming proof of applied intelligence, leverage, and relentless repetition. Attributing these works to extraterrestrial architects does more than misread history. It disempowers humanity. It steals the credit from the master quarryman who could read a bedrock seam, from the chant master whose song synchronized 100 pulls on a rope, and from the society that organized itself around a shared vision for generations. The so-called mystery evaporates when you look closely at the stones themselves. Those precise fits are not the product of laser tools, but of abrasive sand and iterative grinding. Those astronomical alignments required no advanced computers, only careful, generational observation of the horizon with simple sighting poles. The true wonder is not that they had help we cannot understand, but that they achieved so much with tools we can readily comprehend. This reclamation is profoundly empowering. It shifts the narrative from a search for external, magical saviors to an appreciation of internal, human potential. It asks us to reconsider what we are capable of when skill is deepened over a lifetime, when communities align around a purpose, and when patience is measured not in weeks but in decades. The builders of these sites did not possess secrets from beyond our world. They possessed a profound mastery of this one. They understood stone, gravity, geometry, and social cooperation on a level that our faster, more abstract world has largely forgotten. Their legacy is not a puzzle to be solved by imagining outside intervention, but a testament to the monumental heights that focused human ingenuity can reach when it works in harmony with the materials and rhythms of the earth. The chisel's sharp ring meets the soft hum of a three-dimensional scanner, a conversation across 4,000 years. In workshops today, master stonemasons are blending the oldest tactile skills with the newest digital tools, not replacing one with the other, but creating a powerful new dialect. This fusion reveals something unexpected. The core principles that guided the pyramid builders are experiencing a profound renaissance. We see it in the bespoke stone cladding of a modern museum, where each uniquely curved panel is first modeled in clay by hand, capturing the artisan's intuitive feel, then scanned and precisely carved by a robotic arm. The ancient process of creating a soft prototype finds its digital echo, marrying the fluid intelligence of the human hand with the unerring accuracy of the machine. This revival extends far beyond stone. The entire maker movement is built upon the bedrock of tacit knowledge and iterative adjustment. A modern inventor crafting a new device will rarely start with a final, rigid blueprint. Instead, they prototype using three-dimensional printers to quickly create a physical model, hold it, test it, and then adjust the digital design based on that hands-on feedback. This loop of make, test, learn, and revise is the direct descendant of the ancient builders' dry fitting process, just accelerated by technology. The material conversation is still paramount. The designer learns from the weight of the prototype, the flex of a joint, the way light falls on a surface, knowledge that no screen can fully convey. Perhaps the most fascinating parallel emerges in the world of parametric design and digital fabrication. Here, architects and artists do not draw a final form. Instead, they write algorithms, sets of rules and relationships that generate forms organically, much like a crystal grows or a leaf unfurls. A designer might input parameters like structural load, material thickness, and desired sunlight. The algorithm then iterates through thousands of possibilities, evolving shapes that are perfectly adapted to those constraints. This is not so different from the way ancient builders allowed the properties of local stone and the forces of seismic activity to dictate the interlocking forms of a wall. Both are methods of responsive design, where the solution is discovered through a dialogue with the conditions of the problem. This enduring legacy shows that the ancient builders' wisdom was never really about the absence of writing, but about the presence of a deeper intelligence. It was a philosophy of engaged, responsive creation that listened to materials, respected natural forces, and valued the knowledge held in the body. Today, as we stand at the intersection of hand and algorithm, that philosophy feels more vital than ever. It reminds us that true precision, whether in limestone or in lines of code, emerges not from rigid control, but from a thoughtful, adaptive conversation between intention and reality. The silent language of the stones is still being spoken, now finding new voices in the whir of a router and the glow of a screen. The journey from the quarry to the Keystone is now complete. We have walked alongside the master mason, felt the vibration of the stone hammer, and seen the calm truth of the water level. What we discovered was not a single lost secret, but an entire world of intelligence, one built without a single written plan. The breathtaking precision of these ancient sites was not a gift from the stars or a relic of a forgotten super science. It was the hard-won result of cultivated skill, of eyes trained to read the horizon and hands educated to feel the soul of granite. It was born from intelligent observation of the cosmos and the earth, and from a profound cooperation that turned whole societies into a single, focused mind. We have traced the 10 principles of this silent system, from the master template that standardized perfection to the dry fit that discovered it through patient dialogue. We saw geometry become a living toolkit and the Plumb bob become an oracle of the true. We witnessed how an understanding of leverage and balance allowed human strength to dance with multi-ton stones, and how the very organization of a community became its most powerful tool. These interconnected methods formed a complete, resilient engineering philosophy, one where knowledge lived in the muscles, in the chants, and in the shared rituals of the people. This legacy stands as a monumental testament to the power of human ingenuity when it is embodied in practice, passed from hand to hand, and rooted in a common purpose. It challenges our modern assumption that complexity requires abstract documentation, reminding us that some of the deepest understanding is learned by doing and felt in the bones. So let this exploration change the way you see the world. Let it inspire a deeper appreciation for the craftsmanship in the old stone wall, the arched bridge, or the handmade tool. Let it spark a curiosity about the unwritten wisdom in our own trades and traditions, the tacit knowledge that still guides the artist's brush, the gardener's touch, or the mechanic's ear. The ancient builders left us more than monuments. They left a mirror reflecting the profound potential of focused human collaboration. If this voyage into the hands of history resonated with you, we would love to hear your thoughts in the comments below. Consider subscribing to continue unraveling the profound human mysteries of our past together.